It reads as follows: a simplified diagram of an AC generator connected to a 25 ohm resistor is shown. The coil rotates anti-clockwise. Again, name the component that distinguish 18.1. Name the component that distinguish this generator from a DC generator. So we are told to remove the generator, and then we've got two types of generators here, which is a DC generator and an AC generator. So how does an AC generator differ from what? From a DC generator. 18.1. Name the component here. Which component is that one? That will be what? Slip rings here. Slip rings. We know that the AC generator has slip rings, which is KT2 here. And then on a DC generator is split here. Half here. I see a good. And then that is one mark. 18.2, we're being asked in which direction will the induced current flow in the section X, Y of the coil. Choose from X to Y or Y to X. Again, so since this is a generator, what do we use? Which rule? Fleming's right hand rule. Again, generator for right hand. That's good. That's good. Now we have what? We have our generator there, right hand rule, which is this one. Again, we know this is the FBI. Again, this is your force B, field, and I, FBI. Again, the direction of the force of the field, it was from north to south. Again, good. According to this, the guy from north to south is that direction. Again, according to this here, and we are being told this thing is anti-clockwise, like this again. So if it's anti-clockwise, the cycle X little again, but we still keeping the direction of the field the same again. Again. So we've got two correct, the direction of the field and the direction of the force again. Every three which is current. Current is so again. So I from what? From Y to X again. Good. So it over from Y to X. I want to move from Y to X. That is what? That is 2 marks. So guys, 3 marks. Simple 3 marks. Good. And then about the graph below shows the output voltage of the generator for 1 cycle of rotation of the coil. Again, they say define the term root mean square potential difference. Root mean square potential difference. We taking root mean square potential difference is what?
That produces the same amount.
Is the what? Is the
AC potential.
Is the AC alternating current potential difference again.
Is the same amount of electrical energy.
That produces
the same
amount or what?
Of electrical energy.
The same amount of electrical energy as an equivalent to what? Equivalent to what? To DC what? Potential difference. Again. Good. Right again. When we were discussing this thing in terms of graphs, later in highly DC again. High takamani kao AC tabeta majang. So again, so this part, which is what? Which is the maximum for what? For DC. Again, high takamoki in VRMS. By what? VRMS. So this amount of energy, again, when I in here, and I V max. Again, this V max, DC generator ha re tlisa ka kae ka o AC e le kana le eng ka mo e le kana le RMS ya ka mo. So that this is what this means is the AC potential difference that produces the same amount of electrical energy as an equivalent to DC potential difference. This one is equivalent to what? To that one. Ka bona again. Good. And then Berebanale calculate them. Calculate what? The root mean square current in the second. Again, got 18.1 or 18.4. But initially they were told that this generator is connected to a 25 ohm resistor. Again, so bagabata root mean square current. Tamere tole impele. Tamere tole VRMS. Again, because our electrical appliances had the 70C in, had the 70C Vmax. This is a VRMS. Again, got our electrical appliances. So returning VRMS. This formula, where do you get this formula? Formula sheet here. We copy out as it appears on the formula sheet. Root 2 here. Vmax keep kaimo, Philip Kai Vmax, keep kaimo 100 here. 100 divided by divide by root 2. How much do you get as your answer there? 70,71. What? Volts. Right one I get. Good. And then bagabate kana current here. Current. So kana say what? No, not power. It's our R is equals to V over I. Again, give V what? RMS. Give me I RMS. Again, because this resistance is of what? Of an electrical appliance. By what? BT kai 25 VRMS to tell kai 70,71 over what? Over I RMS. We cross multiply here. Cross multiplication will give us what? I RMS is equals to 70,71 divided by what? Divided by 25. How much are we getting there as our? You see what I did there?
Oh, that's one.
2,83 what? Amperes. Are we together, good people? Yes, thank you. And then, Bagari 18.5. Calculate what?
Calculate
The average power dissipated in the 25 ohm resistor here. 18.5, it's 18.5 here. The average power, kana sibisa in, what's what sibisa IRMS kappa VRMS here. Etaba V squared RMS over what? Over what? R. Here. This is one formula, their power. So it's about 70,71 squared over man resistance on a time to 25 a year. And then what will be the answer? 200 watts. 200 watts a year. Or alternatively, you can use or you can say PAV is equals to V RMS I RMS. Again, V keep time 70, and then here we got how much? 2,83 a year. What is the answer there? 200,1 watt, which is almost the same thing again. Or you can use that one again, or you can say P average is equals to what? I squared RMS resistance again. We are in 2,83 squared times what? 25. How much did you get if you use this one? How much do you get? 200,2 watts. So I wanted to. So I wanted to tell you for a value that is around 200. Still correct. And then Bagari 18 point what? 18.6. But the speed of the rotation of the coil in the generator is now doubled. 18.6 Copy the set of x's below in your answer book and sketch the graph of the output voltage versus what? Versus what? Versus the time for 0.1 seconds. For 0.1 seconds. Again, so good people, what do you have? This is what we're gonna do now. You copy as it is. Now, how much do you have here? 0.025, and then whenever okay, 0.05, parallel is 0.075, and then we had what? 0.1, and time is in what? Time is in seconds, and then we have how much there? We have 0, and then we have what? 100, and then we have 200, and then this side we're going to have negative 100, and then we're going to have negative 200 again. Good. So now if you are doubling the rotational speed again, it means what you call your period is again, is so graph here so don't graph T2 kara 0.0.1 again. So it means it will 200. When I get in a look, in a 0.25, I hit point. So it's to moon. Like when I'm tricky it up. So 0 look, 0.05. Is it a guy? Is it a more? Half 40 low. Now I want. In a look, 0.075. I get the next point. I get 0. Yatamo. I get several guy. Man, how we divide that 2 0, it total somewhere more. Again, it has somewhere more. Again, in the look guy who 0.1, we divide that 2, is it a guy who 0.5 by 1. So, here pay, we have 1 and 2. So, 360 today, say 2, because we have doubled the rotational speed. So, I want to guy. The voltage is a double. It's a guy, it's a moon. It's a guy, it's a moon. And then look at the guy who's 0 man here. So this is what is expected if the rotational speed is being doubled. Again, you remember Harrieta ways in which you can increase the induced EMF. We talk about what? Increasing the rotational speed of the coil. Again, we are using stronger magnets and increasing the number of what? Of coils. Again, so doubling the rotational speed will obviously double what? The output voltage. Again, but frequency is by what? So meaning pure rotating air fluid. So we can have two what you call rotations in 0.1 second. So that was what was expected from you guys. That is 3 marks. So the whole question it will 15 marks again. And for us to pass paper 1, just to pass paper 1, we only need how many marks? Only need 45. Only need 45. So with such questions, how you collect all the marks. So any questions from what we have covered so far, good people? Are we fine? Yeah. Okay, good. Thank you.